longer there, but that's fine. I'm very pleased to be here at Knowledge Graph Conference 2023. It's my second time here, and I see some familiar faces. I also realize that I am the last session in this track, and I'm, sandwiched, pun intended, there between us and lunch, right? So let me get going. The title of my talk today is Knowledge Graphs for Contextual AI. To know how to use knowledge graphs for contextual AI, we need to first understand what a knowledge graph is and what the elements of a knowledge graph are, right? So let's start right there. Every knowledge graph has three elements. We have data, we have relationships, and we have semantics. Let's dive a little bit deeper into each one of those. First of all, data. There are many ways to classify data. One way is we have structured, unstructured, and semi-structured data, right? We all know that. We can also classify data based on relationships. So we have what we call small and wide data. That is data that has one-to-many relationships, or more often than not, many-to-many relationships. We also have deeply, deeply hierarchical and recursive data. And then we can have hidden data, data that's that's hidden, and it only becomes it only shows up because it's connected to another piece of data that's already visible, right? So you uncover hidden data using relationships. These are all what I call complex data, data plus relationships. Okay, so that's a perfect segue to the next element, and that's relationships. Now, relationships provide the first level of context to data. We call this dynamic context because when you take data and you throw it into a dynamic structure like a graph store, for example, you get a structure that's connected contextually to all of its neighbors. The neighbors are connected to their neighbors, and the graph grows and gets richer and richer as more information is added. So you can see here that we're adding context dynamically. Okay, so I just mentioned a graph store here. Complex data, data plus relationships, are very are hard to analyze using traditional technologies. Here I'm talking about SQL and NoSQL databases. So if you're going to build a knowledge graph, the advice is use a graph store, right? In a graph store, relationships are naturally captured and they're stored alongside data. So if related entities are physically linked. So accessing relationships is just as immediate as accessing data itself. In a graph store, you simply read relationships from storage. Okay, so that is as far as relationships are concerned. Let's turn to the next element, and that's semantics. If you have data in a graph and you add semantics to it, you get a knowledge graph. Okay, so what exactly is semantics, though? Semantics basically means meaning, and it confers context to data. Okay, there are many, many different types of semantics, and shown on this slide are just 4 of those. I'm going to walk you through each one of these very briefly. I'll start from the simple and go to the complex. The first one is tagging, categorization, and classification. We all know what that is, so I don't need to describe that any further. Next, we have entity resolution and analysis. Entity resolution is all about determining whether records from different data sources represent the same entity. Okay, where is this important? Wherever consistency of data is required. For example, if you're in a bank, you want to know if any of your clients are committing fraud, you would use entity resolution to identify and resolve it. Okay, so the third type of semantics we have is controlled vocabularies. And they too run the gamut from simple to complex. So we have synonym rings and taxonomies. These are considered lightweight. And then we have ontologies that are considered heavyweight because they have better inferencing power. But then keep in mind that, when you're when you have to build and maintain an ontology, it's very time and resource intensive. So again, you're advised to proceed with caution if you were to embark on building an ontology. All right. And then last but not least, we have artificial intelligence. That's a very vast topic as well. We all know that it covers everything from machine learning and deep learning to natural language processing and natural language understanding. For the purposes of As far as knowledge graphs are concerned, AI is important for a process called knowledge graph completion, whereby missing entities and links are added, using entity resolution and or embeddings. Interestingly enough, there's a talk later on this afternoon. It's a virtual session. It looks very, very interesting, actually. It's from 2 to 2:30 in the deep learning track. And they're going to be talking about using embeddings for knowledge graph completion. So if anyone's interested, I think that'll be a good talk. All right. So let's get back to why semantics are important. Semantics are important because they add the second layer of context to data. And we call this, and so we say that knowledge graphs have deep dynamic context. So dynamic comes from the relationships, deep comes from the semantics, right? So if there's one takeaway I want you to, go home with as far as this section is concerned, it's that knowledge graphs are all about context, and more context, right? And context is important because it increases predictive accuracy of analytics and especially machine learning. And that's what I'm going to focus on for the rest of my talk right now. All right, so let's take a look at knowledge graphs for contextual AI. Now, as we all know, context is an absolute must for AI ML systems, and knowledge graphs provide this much needed context in two different ways. I've already mentioned it. It's via semantics and via relationships, right? So just let's take a look at the first reason, via semantics. Semantics are encoded alongside data in a knowledge graph, thereby making data smart, but much more importantly, they confer context to data. Okay, so that's the first way. And then let's take a look at relationships. As far as relationships are concerned, context is defined as all the paths or relationships from one particular entity to all other entities in that network, right? So the closer two entities are, the more related they are, and the more context they provide each other, right? So again, I'm trying to paint this picture of why knowledge graphs are so important and how they provide context, right? Now, relationships have a second benefit. Relationships are the best predictors of behavior. And, but unfortunately today, most data scientists or data science approaches do not use relationships because there is, it's not easy to process network structures, right? And the problem with that is that, if you go to a data scientist and you say, hey, if you talk to any data scientist, they'll tell you that if only they had more data, their models would be so much more predictive, right? Well, guess what? Relationships provide that more data that data scientists are looking for, and they also provide more data variety, right? And we all know in machine learning, the more data you have, the higher the data quality. The more data variety you have, the more data accuracy, right? And so, we bring it back to this point where relationships are important for not just providing context, but also providing that extra data variety and quality that machine learning models need. So let's take a look at how knowledge graphs can enhance every step of the machine learning process. Okay, all the way from data sourcing to and creating machine learning models to predicting to increasing predictions as well as applying results. All right, so let's take a look at the first step, and that's data sourcing. Now, if you have a machine learning model, but you don't know where the data to train it came from, you can't trust that machine learning model, right? And so what knowledge graphs do is they allow you, knowledge graphs can be used for data lineage and to track data that feeds into a machine learning model, where the data came from, how is it transformed, where was it used, who used it, and so on and so forth, right? So that's where knowledge graphs play a very important role. In the second step of data discovery, knowledge graphs, play an important role as well. You have the data, you can track your data now, but can your data scientists get to it quickly? Okay, so knowledge graphs can be used to find data quickly and efficiently, and they provide another important function. They can also be used to identify trends, patterns, and hidden data, data that you didn't know existed before because you never knew about it, right? So here again, knowledge graphs provide that the notion of data discovery, where you can have more data than you originally thought that you had, right? Okay, next, creating predictive models. Now, training a machine learning model requires providing a machine learning algorithm with training data and significant features to learn a new function and make predictions, right? So knowledge graphs uh, provide two main functions here. One is context. I keep coming back to context. Without context, training machine learning models requires exhaustive training, prescriptive rules, and only applies to a small set of applications. Okay, so that's the one advantage to using a knowledge graph, because it provides that context. The second is that knowledge graphs can be applied for feature engineering using graph algorithms and embeddings. Okay, and as I mentioned earlier on, relationships are the best predictors of behavior. So using connected, contextualized features maximize the predictive power of machine learning models, right? And then lastly, analyzing predictions and applying results. Once a machine learning model has been developed, we need to know if that machine learning model is useful and if it's making the correct predictions, right? Knowledge graphs incorporate relationship information and allow for easy graph investigations. So the next few slides that I'm going to talk about right now would exemplify this better, because they showcase how different organizations are using knowledge graphs for data lineage, data discovery, and data analytics. Okay. All right, so the first use case that I would like to share with you is data lineage and tracking for governance and compliance at UBS. The challenge at UBS was that they needed to track and ensure transparency of all the data flows that fed into their risk reporting mechanisms, so that they could be in compliance with the BCBS 239 regulations. Those are part of the SOX regulations, and we all know that SOX regulations are very important for the banking or the financial industry, right? So what they did was they used a knowledge graph to build a data lineage and governance tool that they then used to track all the data across the organization, monitor its quality, discover any errors, and then trace it back to the source, so that they could rectify it. So with the result that UBS managed to get complete visibility into all of their data flows, enabling UBS to be compliant with the stringent BCBS 239 regulations. Now, at UBS, data lineage was used for data governance and data compliance. In machine learning, data lineage is important because it shows exactly where and when data was captured, okay? Where all the data has moved, from sourcing, staging, and sandboxes, all the way to data warehouses and data lakes. How data was transformed, who and how users use that or touch that data, right? So data lineage allows, in machine learning, allows for tracking data quality. And we all know how important that is for machine learning, okay? So next use case is using knowledge graphs for data discovery, increasing findability at NASA. Now, the challenge at NASA was, while they were working on a mission to send Orion into space, NASA engineers found that there was an error in there was an issue with its uprighting mechanism. So rather than spend years redesigning the entire uprighting mechanism, NASA engineers went to NASA scientists and asked for a solution. So what NASA scientists did was that they used a knowledge graph to comb through millions of documents, scientific literature, their lessons learned database. This is a repository of mission reports of all their missions, successful and unsuccessful. Of geospatial data, IT logs, and so on and so forth. and identified that there was a similar upriding mechanism in the Apollo spaceship. So, they reported that back to the NASA engineers, who then resolved that issue with their upriding mechanism from the knowledge that they gained from the Apollo spacecraft, and saving 2 years worth of time, and $1 million of taxpayers' money, $1 million of taxpayers' money, right? So at NASA, of course, the knowledge graph was used for semantic search to be able to find information quickly. With machine learning, knowledge graphs are important for data discovery. They really help data scientists get to that data very quickly and efficiently. And they also help with uncovering trends, patterns, and unexpected results that they may have otherwise not known about. Okay, and then the last case study that I want to share with you is using knowledge graphs for data analytics, improving patient outcomes at AstraZeneca. AstraZeneca, one of the largest pharmaceuticals in the world, realized that no two patient journeys are exactly alike, but they wanted to use patient journeys in some way to be able to help their patients. So what they did was they used a knowledge graph. They used a combination of a knowledge graph, graph algorithms, and machine learning to analyze over 4 billion patient records that they had collected over a three-year period. That included things like doctor visits. Let's see what else. Tests, measurements, diagnoses, prescriptions, and many other variables. Okay. So the first thing they did was they identified patient journey archetypes using graph feature engineering embeddings to, as input into machine learning models. Okay, and then they utilized two different algorithms. One was PageRank to identify influential touch points that allowed them to intervene at the earliest moments in patients' journeys, so as to improve patient outcomes. Okay, so that was the first, to significantly improve their patient outcomes. So that was the first algorithm. The second algorithm they used was community detection algorithm. Here, what they did was they used that to cluster patients who had the same diagnosis and were given the same drug into two different clusters. Okay, one cluster that's of patients who saw benefits using that particular drug, whereas the other cluster was patients who did not see a benefit using that drug. Okay, so keep in mind again, same diagnosis, same patients, two clusters, benefit, no benefit. Okay, interesting point here that I'd like to make is that AstraZeneca research scientists did not need to understand the mechanism of action of why one group benefited and the other didn't. And if you know research scientists, they're always interested to know why there's this mechanism of action, okay? All they needed to do was to see this, all they needed to look at was this embedding in this low dimensional space, because it was so packed with information that it naturally broke out into these two clusters, okay? So now when a new patient came along, what they would do was, they would identify this new patient's journey. They would then embed it and see which cluster it fell into. If it fell into the cluster that showed benefit, this patient was given a prescription and sent home. Hopefully, would have seen benefit from that, right? Because there were similar patients. There were patients in that cluster that saw a benefit. Now, if there was a patient who came in and fell into the no benefits cluster, they wouldn't give them this drug. And so, it was a nice way for AstraZeneca to actually target patients and recommend the drug only if it was of value to or of benefit to the patient, right? So the thing about this is you're getting to personalization of drugs, which is what everyone's been trying to do. That is the beauty of what this knowledge graph allowed you to do with data analytics. So here, knowledge graphs provided the gateway to powerful graph analytics. We had embeddings for graph feature engineering, and we use graph algorithms for impactful analysis, right? And I have 30 seconds left, so I'm going to finish off very quickly by saying this. Knowledge graphs are super powerful and super versatile, and they're the only solution to today's complex data, data plus relationships problems that every organization faces, right? So I want to say with that, what a better way to say that than in a knowledge graph conference. I'm ready for any questions. Thank you.
I'm curious, in that AstraZeneca example you gave, you mentioned personas and archetypes. Could that be used to personalize like an individual patient's experience?
It was ultimately used to individualize the patient's drug treatment. So, when it fell into the two clusters, basically, if the patient saw benefit, they were given if they fell into the benefits cluster, I'm sorry, they were then given the prescription. Otherwise, they weren't. And they've been tracking them for a while now at AstraZeneca, and they seem to have very good results with that. Yeah.
Thanks.
From AstraZeneca, so comment on this.
You want to comment first? Okay, and then we'll bring it back.
I hope I'm not making this up.
Well, I mean, the one thing that I would caution, and we should probably talk about this offline, is you can do that for a physician recommendation system, but the physician has to make the call. The algorithm's not going to make the call. I mean, this is not a GXP system, so that would be as far as you could take it.
Thank you very much for pointing that out. Yes. I don't want to suggest that they were given the drug. Obviously, the doctor has the final call, right, and needs to make that. Yeah. Thank you very much for pointing that out.
Hi, excellent talk.
Thank you.
So I have a question on the data lineage and provenance you mentioned, and you said knowledge graphs could, solve that problem. So I want to push back on that a little bit because, in knowledge graphs we have assertions, and anybody can make an assertion about anything, right? So even the fact that this came from this particular location. So unless they're signed and verifiable in some means, I want to say that knowledge graphs are not the only solution. Maybe it's part of the solution.
Absolutely.
Right.
I'm not saying that you use only knowledge graphs.
Sure,
No. There's a lot more to it. Data lineage and governance is a big topic on its own, right? So fair enough, you can push back on me, but I don't believe I said knowledge graphs are the only solution.
Yeah.
I said that in my last statement, though.
Okay, thank you.
Yeah.
Okay, well, if there's no more questions, please join me in thanking Maya.
Thank you so much. I made it before lunch. Take this. No, thank you so much.